14 billion years ago, a single instant kick-started our entire universe. This dramatic Big Bang gave birth to the physical realm. Over time, its products evolved into the present-day universe. From the smallest atoms and molecules to the largest stars and galaxies, from solar systems and planets, including ours, to all life contained within it. September 2008, an experiment designed to simulate the Big Bang is about to start up. The scientific world buzzes with excitement, even as doomsday predictions throw up grim possibilities. Will the Large Hadron Collider be modern-day science's biggest blunder? Or will it be an unprecedented window into our mysterious universe? That's a question of science. The Large Hadron Collider, or the LHC, has been over a decade in the making. Led by CERN, or the European Organization for Nuclear Research, its construction has taken a collaboration of 10,000 scientists from over 100 countries, including India. But why has it held the physics community in such nerve-wracking anticipation? The LHC promises a never-before peek into the very fabric of the material world, answering questions we've been asking for thousands of years. It all began with a simple inquiry. What is everything made of? The ancient Indians and Greeks first proposed that everything material or matter could be broken down into indivisible units. These were called Anu in Sanskrit and atomos in Greek. By the 18th and 19th century, scientific experiments had confirmed this. In the late 19th and early 20th century, scientists went further into the atom. They found subatomic particles like electrons, protons, and neutrons. But particle physicists wanted to go deeper still. They postulated particles like quarks, which make up protons and neutrons, and proposed a category called leptons, under which electrons were classified. Besides these particles of matter, forces were proposed to govern them. These were gravitational, electromagnetic, and weak and strong nuclear forces. By the early 21st century, technology had advanced enough to experimentally confirm all these. In fact, there have even been discoveries of new particles like muons and neutrinos. Slowly but surely, the discoveries were piling up like pieces of a jigsaw puzzle. But if all these pieces made up the natural world, the question arose: what was the big picture? Today, there are many proposed big pictures to unite particles and their properties. Of these, one emerges as the most probable, the Standard Model of particle physics. Broadly speaking, it consists of 12 basic blocks of particles that construct all of matter, 4 fundamental forces, 3 of which are governed by 4 force carriers, and the critical Higgs boson to explain how everything acquires mass. So far, this is the most successful model to explain the natural world. And it took several thinkers from around the globe, including India, to put it together. Their work collectively spanning more than a century. But how can these theoretical pictures be proven by scientific observation? Over the last century, scientists have built experiments to look deeper and deeper inside the atoms by crashing them into each other. The LHC, or the Large Hadron Collider, is only the latest in a long line of such experimental machines known as particle accelerators. Particle accelerators are machines that are designed to smash atoms or subatomic particles into a chosen target. This smashing happens by speeding up particles to extremely high speeds. The higher the speed or energy, the bigger the collision. But why make particles collide? That's because particles that collide in extreme energies create new products and phenomena. By studying these, we can piece together how the original products were formed. The first particle accelerator was built in 1932 by John D. Cockcroft and Ernest Walton at the Cavendish Laboratory in Cambridge, England. They found a way into the nucleus by bombarding lithium atoms with accelerated protons. Since then, particle accelerator designs have gone through many avatars. Each generation of accelerators has reached higher and higher energies in order to crack the tiniest realms of the subatomic world.
Delhi for centuries has nurtured many kingdoms and rulers. These kingdoms have left us several significant monuments with an incredible history to tell. Among these monuments is one which is in the midst of posh bungalows in Hauz Khas area, the Chor Minar. Built under the rule of Alauddin Khilji, telling a statement of his rule, is believed to have stood out as a deterrent for thieves and thugs who attempted to venture in his kingdom. Built in 13th century, the pillar is made of rubble masonry and stands at the center of a platform. Each of the four sides of the platform has three arched recesses with a doorway on one side leading to a spiral staircase. The pillar, also believed to be known as the Tower of Thieves, was used to display the severed heads of the thieves and thugs through its 225 holes.
Today, the Large Hadron Collider, or the LHC, is the highest energy particle accelerator in the world. The circular LHC accelerator stretches across the border of Switzerland and France, between the Jura Mountains and the Alps. As the name suggests, this particle accelerator crashes hadrons, a class of subatomic particles which are made up of quarks, for example, protons and neutrons. By crashing into each other, the hadrons decay into other particles and energies, which scientists can closely study.
We are really having here the most powerful microscope in the world. And with this most powerful microscope, we look very deep into the microcosm. And when we look very deep into what are the components out of which we are consisting, we are also looking at the early universe, or the development of the universe.
One of the biggest challenges for this powerful microscope is to confirm the standard model of particle physics, or forge the way for an entirely new kind of physics. But what exactly goes on inside the circular LHC?
In simple terms, it is a machine which accelerates particles. We take a stone and we tie it on a string and we turn it around, we swirl it around, and so it's gathering energy. In a very similar manner, we take protons, which are nothing but hydrogen nuclei.
Before entering the LHC, packets of protons are obtained after stripping hydrogen atoms of their electrons. These packets are energized with powerful electric and magnetic fields, which steer and guide them. They're made to go faster and faster until they have extremely high energies. The packets of protons now enter the LHC ring and are split into two beam tunnels, one packet in the clockwise direction and the other packet in the counterclockwise direction. The two counter-rotating packets or beams are now on a collision course at 99% the speed of light, the beams crash into each other, recreating the more famous bang in history, the Big Bang, albeit at a minute fraction of its ferocious energy. This harmless version of the Big Bang can tell us about the birth of all matter and, in fact, the universe itself.
Let's take a simple law of physics. Matter and antimatter should exist in equal proportions. So why are we there at all? We should have been annihilated. There are certain broken symmetries in nature whereby you have a little extra matter than antimatter. So it's that little extra that we are all made of, and the whole universe and the galaxies are made of. Now, how much is that extra? And is all what we see around us everything?
We are getting into a new era because the past 40 to 50 years have allowed us to describe, partially understand the visible universe. But if you look out in the universe, this is just 5% of the universe. 95% we don't know very much about it. I would call it the dark universe. And I hope that with the LHC we get the first step into this dark universe, and that would shift everything.
The LHC is a marvel of global technology and engineering. Burrowed at an average depth of 100 meters, this 27-kilometer circumference consists of 2 tunnels to zoom particle beams, either protons or lead nuclei in opposite directions. These tunnels are literally the emptiest place in the universe. There's complete vacuum. Nothing but colliding particle beams can whiz around, meeting at 4 collision points. Here, teams have set up 4 experiments called CMS, ALICE, ATLAS, and LHCb. So what exactly drives these beam of particles through the LHC ring? The answer: more than 9,000 current-carrying electromagnets. Together, they steer beam particles through vacuum, making sure they stay their course and don't bump into anything except the counter-rotating beam. In doing so, they exert a massive magnetic field of 8.3 Tesla. That's nearly 1 lakh times the Earth's magnetic field. How does one possibly construct such a huge magnetic field using current-carrying magnets? The answer is superconductivity. A normal current carrier, like a wire in our homes, loses energy through resistance. But superconductivity can give it the power to overcome any resistance. That means the same wire, once made superconducting, can carry much more current than before. The LHC's superconducting wires carry about 12 to 13,000 amperes. That's nearly 30,000 times the current flowing in a single 100-watt light bulb. How is this superconductivity achieved?
The idea is that since we are going to put so much high current, it is a cryogenic structure, and to make that we need to build a cryostat. So this, all these other things right up to the blue tube is the cryostat that we did on an industrial scale. Each delivered magnet had to be cryostated with all these special insulation blankets and material.
What exactly is cryostating? It's the process of using liquid helium to plunge temperatures so low that it paralyzes any resistance to current. Suddenly, a normal conductor becomes a superconductor. And so, the superconducting magnets are kept at 1.9 Kelvin or minus 271 degrees Celsius, making the LHC not just the coldest place on the planet, but in fact, the entire universe.
We are in the hall where we tested all the LHC cryogenic magnets. We tested all those magnets on the surface before putting into the tunnel, and the Indian role was absolutely essential.
From 2001 to 2008, 100 Indian technicians and engineers streamed into this hall to test each and every one of the LHC's superconducting magnets before they were fitted into the underground tunnel. The teams came from India's premier institute, the Rajya Center for Advanced Technology, or RRCAT, Indore. Teams from RRCAT Indore also helped build the LHC's corrector magnets, which, true to their name, ensure that beams stay on their correct track at all times. Far from home, the teams worked doggedly in batches for nearly 7 years, striving hard to get the LHC ready in time for its big debut.
First up, National Digital Communications Policy 2018.
So what it aims is to provide a ubiquitous, affordable, convenient communication infrastructure to the people of India.
Let's take a closer look at online incorporation of limited liability partnership.
I welcome this move because I think LLPs are very good ideas in a country where a lot of young people are trying to be entrepreneurial, and making it simpler for them to do that is not a bad idea at all.
You can get a title for your company, the partnership. Let me not call it a company, partnership. It's similarly incorporation certificate, as also your DIN number and TAN or a PAN registration to be done online, which is earlier it was not covering LLPs.
September 2008, a landmark moment for the LHC collaboration and physics community around the globe. The Large Hadron Collider launches its very first beam of protons. The colliding beams will set a new energy standard for experiments. They will also answer the fears of catastrophes, like the creation of a black hole that could swallow planet Earth. For a moment in the control room, scientists hold their collective breath, and then a vote of thanks is given out in French, translated as "Thank you to the whole world." The LHC runs successfully, its safe collisions proving every doomsday prophecy wrong. But within 9 days, a major accident would destroy 50 magnets and bring it to a halt. Once again, Indian scientists stepped up to help. They reunited with their international counterparts and helped put the accelerator back on its feet again.
This was a very, very important help from India, so that was very much appreciated.
Since November 2009, the Large Hadron Collider has been back in action and functioning better than ever.
We are at the CERN Control Center or CERN Control Room. This is where we have all the accelerators of CERN regrouped under one roof from the purposes of operating and controlling these accelerators. All the accelerators are divided into 4 satellites or 4 islands.
The 4 islands in the control center track the journey of particle beams from creation to collision. The beam is first accelerated in an accelerator called LINAC 2. It then passes through a ring called the proton synchrotron or PS. Then it enters an accelerator called the super proton synchrotron or SPS before finally reaching the LHC. At each level in this journey, the particle beam gathers speed and energy until the protons are traveling at 99% the speed of light. A successfully running accelerator means successful particle collisions. But just how many are there? Nearly 40 million collisions a second to be precise. Each collision leads to the birth of countless new particles and energies for physicists to study.
So in the last year of running, the LHC produced something like 25 petabytes of data. This is 25 million gigabytes of data.
Exactly how much data does this amount to? Quite literally, more than a mountain. In fact, if you were to stack it all up in CDs, it would be taller than twice the height of the world's tallest mountain, Mount Everest. It raises an interesting dilemma. How can this volume of path-breaking information be made available to scientists across the globe?
So even though we have a big computer center here, it's not enough to analyze everything. So what we do is, it arrives here, it's stored on tape. First analysis is done with some of the machines that you can see behind me, and then we distribute the data that we have all around the world.
The LHC takes a complex computing problem and solves it by breaking it up into smaller jobs that are distributed around the world, including India. The epicenter of this novel solution is CERN itself, which happens to be the birthplace of another information sharing revolution that you might know as the Internet. And so is born the WLCG, or Worldwide LHC Computing Grid, a one-of-a-kind network with 3 levels or tiers, where not just information but computing power is shared by a global collaboration. Tier 0 is at CERN, which handles 20% of the total LHC computing data. From here, it fans out into 11 Tier 1 centers, which handle the next 30% of the data. The remaining 50% is handled by 250 Tier 2 centers. 2 of these Tier 2 centers are in India, one at the Kolkata's Variable Energy Cyclotron Center and the other at Mumbai's Tata Institute of Fundamental Research.
And you can see it here, starting at CERN near Lake Geneva. And if I zoom out, you can see the arrows are data transfers. And you can see transferring across Europe. And if I zoom out further, you'll see data transfers heading towards Asia. This shows how an Indian site, in this case Mumbai, is connected to the global physics analysis for LHC.
Many hail the WLCG as the next big thing in computing. But when it came to developing this next big thing, Indians had a big hand. Software developers at the Bhabha Atomic Research Center were involved in developing systems that monitor how well the grid functions and ensures it's in working condition around the clock. For the last 3 years, the LHC has enjoyed a very productive run. Its high point coming on July 4th, 2012, when scientists announced the discovery of one of the most elusive building blocks of the Standard Model, the Higgs boson.
We have observed a new particle consistent with a Higgs boson. As a layman, I would now say, I think we have it. You agree? Yeah.
This discovery pegs another piece of the jigsaw puzzle into place, bringing the big picture a step closer to completion. It's a historic achievement that would have been impossible without contributions made by countries like India. But that's not where the story ends. As all good science does, the LHC will continue to push its global collaboration into the next paradigm of questioning. In the bargain, India will stand to gain a lot.
I think that it's a win-win because the technologies are really state-of-the-art. We get to be exposed to developing technology as such. So we are developing skills which are far ahead of their time. far ahead of any industry that is able to produce at this moment of time. And we also develop the infrastructure and the network in the way we want to do science and in the way we want to take science to another level in our country.
If you'd like to share your feedback on today's program, please send your suggestions and comments to Vigyan Prasar, C24 Qutub Institutional Area, New Delhi 110016, or you can mail us at info@vigyanprasar.gov.in.